category. So I request you, sir, please share your screen and start your presentation. Thank you, sir.
Very good morning, good afternoon to all of you. And my topic is PSO-based MPPT controller for photovoltaic solar system. I have chosen this PSO. The full form of this PSO is particle swarm optimization. The program, the BFTB program, is on artificial intelligence, and it's a big umbrella. And this PSO comes under that umbrella. And title of this session is that application of AI in renewable integration. So that's why I have chosen this photovoltaic solar system. And one specific point I have chosen, that MPPT controller, which is integral part of any solar photovoltaic system. So why PSO has been chosen for MPPT controller when already existing MPPT controllers are there for photovoltaic solar system? So there will be some advantage, something will be there, and some problem with MPPT controllers would be there. And we will see whether we can provide a solution by this PSO to the existing problem of MPPT controller. Not only solution, but simple solution should be provided. Then only the use is justified. So before we start why PSO is used, why, I don't know the background of the participants. There are a number of participants are there, 50 participants are there. So I would like to just go on review of the basics of that solar photovoltaic and MPPT and the problem associated with that, so that we can understand the use of PSO in the case of maximum power point tracking in solar system. By the way, I'm going to start with a basic photovoltaic array. You all have seen that photovoltaic array. So photovoltaic array, this figure represents the photovoltaic array. Photovoltaic array is the combination of different photovoltaic modules. There are three terms. We should be familiar of this three terms, that is PV cell, photovoltaic cell, PV module, and PV array. Actually, this PV cell is the basic elemental part, the main element, the fundamental element of any PV array or photovoltaic array. Now, this PV array, you just see, if this is the power plant, any particular solar power plant, and huge PV array is shown. So now if we go to the market and try to purchase that PV array, we won't get it. Actually, the easily available part of this PV array is this PV module. Solar cell we can also purchase, but it is not easily available. So in the common market, this PV module is available. Now solar cell is connected in series. Solar cell is basically a simple PN junction, not simple PN junction. It is a type of PN junction which is different from the normal PN junction diode. And what is the difference? I'm not going into the deep detail. A small difference I would like to mention, that the layer of that N type of material in PN junction for solar cell is very, very thin, so that the solar irradiance, solar photons can penetrate that N layer and reach to that junction, PN junction, and release that electron hole combination, and current will flow. This is the fundamental concept of that solar current or solar power, solar voltage in solar PV cell. So we have to remember this thing only, that thin layer, thin N type of layer is there. Solar photons comes and penetrate that thin layer and goes to the PN junction and releases that electron ion pair, which is the main basis to form that solar current. Now, because this is a small PN junction, so the voltage produced by this solar cell is very small. That is, say for example, 0.5 volt if it is silicon cell. Now 0.5 volt cannot be utilized in proper application, for common application, any application. So what to do? So these solar cells of 0.5 volts are connected in series. Number of solar cells are connected in series to form this module. See, okay. Now this module is available of different ratings of these modules are available. We purchase these modules, and these modules are again combined in series parallel combination. This, see, this white border is showing one module, and this is small squares are showing solar cells. So by using series parallel combination of these modules, we form a typical PV array. We can see here, so these are four modules and one solar cell 0.5 volt. So there are eight solar cells in this column, and 1 2 3 4 5. So there are 36 solar cells. So 36 multiplied by 0.5 is 16 volt. So 16 volt, 16 volt, 16 volt, 16 volts. Four modules are there. They are connected in series parallel combination to find out the PV array giving VPV, the PV array voltage equal to 32 volts, and the current supplied by this PV array to the load will be the combination of this current and this current. IPV will be equal to IA plus I. Now come to the characteristic. So this characteristic, this PV characteristic is the characteristic of a PV array or PV module if the solar irradiance is constant. What is the meaning of constant solar irradiance? Means this solar irradiance, by the way, solar irradiance is representing the power which is coming from the solar and on the surface of the PV array. So if the solar irradiance is constant solar irradiance, same solar irradiance is there on each and every module, then we say that constant solar irradiance. So for constant solar irradiance, these two characteristics are there. Two types of characteristics are there: current characteristic and power characteristic. So when the two terminal across the solar PV array, this one is open, VOC, open circuit voltage is there, and current will be obviously zero. Now, if the two terminals are short circuited, the current which will be flowing is known as short circuit current, and obviously voltage will be equal to zero. So this is the characteristic, one characteristic which is on standard test condition. These terms actually very common terms that should be in our mind if we are dealing with any PV system. So standard test condition means if we go and purchase any PV module, this rating will be given that 150 watt module, say for example 150 watt module we are purchasing. So this 150 watt will be at standard test condition, that means 1000 watt per meter square irradiance and solar cell temperature equal to 25 degrees centigrade. Okay, now if the solar irradiance, by the way, one more term here is introduced, that is insolation. So insolation is generally confused by the irradiance. It is understood as the synonyms of irradiance, but it's not the fact. Actually, in the initial days, I was also confused with these two terms, insolation and irradiance. So basically, solar irradiance is power per meter square on the surface represented by S. And insolation is the energy counterpart of that solar irradiance. So it is joule per meter square or watt second per meter square. So when the solar irradiance is decreased, the current is decreased. Okay, current is decreased, and the open circuit voltage is slightly decreased. Now come to the second curve, that is power curve. This curve is the power versus voltage. Okay, so at zero voltage, at short circuit current, the power will be multiplication of this current and voltage. So power produced is zero. At open circuit voltage, obviously no current is flowing in the load. So multiplication of this voltage and current will be zero. So power will be zero. So when we proceed from this point to this point, when we increase from short circuit voltage to open circuit voltage, there is a point, there is only single point at which maximum power is generated. Okay, and the point, the voltage is known as VMPP, voltage at maximum power point, and corresponding current is known as IMPP. This I'm not showing here, it's not shown. So this is IMPP. So specification of any module will be having ISC, VOC, IMPP and VMPP. Okay, and this is for solar, constant solar irradiance. Now what will happen if solar irradiance is not constant like this? If it is like this, here the solar irradiance is not constant, so that condition is known as partial shaded condition. We can see a PV array, many modules are there. So we can see the lower one, the half, more than half is shaded, and the upper one is fully illuminated or fully radiated. Here, half with this column is also shaded, and in this module, some small shadings are there. Okay. So if this type of condition, which is inevitable, obviously, you cannot stop this type of condition. Clouds are there, trees are there, so there are different conditions. So if partial shaded conditions are there, so what will happen? This is the schematic representation of the PV array under partial shaded condition. These modules are actually getting full irradiance, white one. This is having small shading. This is having again even more shading, and these two modules are heavily shaded. Okay, so there are two diodes which are shown here. This is blocking diode and bypass diode. Now these blocking and bypass diodes are must in any PV array. Why? Because in partial shaded condition, there is a phenomena. There is a phenomena that the modules which are less irradiated, which are getting less irradiance, they will be developing, they will be actually, power will be discharged, energy will be discharged in those modules or cells, and red hot spot will be created, and it will damage that cell, and eventually it will damage that module. So by using bypass diode and blocking diode, we prevent that type of damage of hot spot due to hot spot under partially shaded condition. Now in partially shaded condition, what will be the solar PV characteristic? It will be like this. Okay, so in normal constant solar irradiance, there will be only one peak like this. This is one peak, and in partially shaded condition, there will be different peaks. Okay, so these two are known as, this is particular case I'm showing, these two are known as local MPP, and this one is global MPP or real MPP. Okay, now the solar, come to the actual system. I'm showing here that grid connected system. Actually solar system are two types of system, that is it is operated in islanded mode or standalone mode, or it is being operated in grid connected mode. I'm showing here that grid connected PV system, because in grid connected PV system, it is possible to operate the PV array under MPP condition, MPP operating condition always. There is no condition. In a standalone mode, what happens? The load is having some demand of power. So that power is to be produced by that PV panel. Okay, so you cannot operate PV panel or PV array at MPP always when it is connected in islanded mode or it is connected in standalone mode. Okay, of course there are MPPT controller in a standalone mode as well, because the battery is there. So for some time you can operate the PV array at maximum power point condition when load demand is there. The load combined with the battery demand is there. But if battery is fully charged, load demand is reduced. So now the PV operated cannot be operated at maximum, PV array cannot be operated at maximum power point. So it has to be reduced, the operating point is to be changed from that maximum power point. But in grid connected system, the power which is being produced by PV panel can be injected into the grid, because we are considering it as infinite bus. So basically two types of grid connected systems are there: two-stage system and single-stage system. The lower one is two-stage system. Actually this one is very common conventional system. More conventional system is two-stage system. But nowadays with large power plant, the single stage system is coming into picture and it is being utilized. So in two-stage system, Actually, grid is three-phase grid or single-phase grid. It is AC power. So the power which is being produced by PV array is DC. So it is to be converted in AC. So in the two-stage system, first DC to DC converter is there. Then this point, this link is DC link, and then DC to AC converter is there, and it is connected to the grid. Now these two stages are used because the voltage of this PV panel is not matching the grid. So we have to boost up. Okay, we have to boost up the voltage, because if we are using this simple AC converter, DC to AC converter, we cannot match, because inverter are inherently buck converter. So DC to DC converter is needed and DC to AC converter is needed. Now in two-stage system, there are some advantage of two-stage system, but the disadvantage is there are two power electronic power processing stage. So there are losses in two stages, so losses are increased. So if the rating of the power plant is increased, so obviously this loss is a significant amount. Okay, so we go for the single stage, that is single DC to AC inverter, and filter is needed. And obviously for connecting to the grid, we can use the transformer if extra large PV plant is there. Now, what is the advantage in two-stage system? The two-stage system advantages, the advantages in two-stage systems are, actually there are different controllers which are used to for the proper power flow from the PV array to the grid. So MPPT controller, I'm showing only one controller in this slide. There are many other controllers that are PLL, that grid synchronization, and voltage controller, which controls the voltage of this link between DC and AC converter, DC and AC converter, and current controller, which controls the power flow, actual power flow, reactive and active both power flow from PV panel to grid. So if two-stage converters are there, so these controllers strategies are divided in two parts actually. So the controller strategies become simpler. So MPPT controller is operated on this DC to DC converter, and other controllers are operated on this inverter. And in single stage system, all these controllers are integrated, are cooperated in interlinked behavior, okay, at one stage only. So there is complexity in controller design, but for higher power rating PV plant, the losses are more important than that complexity of that controller strategy. So this part we are focusing on this MPPT controller. Continuously we are sensing this current. I'm not showing this MPPT controller here. We can assume that MPPT controller will be here. Continuously we are sensing the voltage and current at the output of PV panel. Okay, it gives some reference, how much voltage is to be there at this point. Okay, and that voltage should be that voltage at maximum power point. Okay, so MPPT controller senses the voltage and current regularly, and accordingly it gives the reference. Accordingly, the voltage controller of this part will settle this voltage, PV array output voltage, equal to VMPP. So it is continuous process and it is always being tracked. So in DC to DC converter, the MPPT controller will give the reference duty cycle, or in DC to AC converter, the MPPT controller will give simple the voltage reference to the voltage controller. Okay. So maximum power point, what is MPPT method? We have already discussed that it is to track maximum power operating point on PV characteristic. Now most common methods, very simple methods, basics methods are perturb and observe, P&O, and another method is incremental conductance. One should have the knowledge, the idea about these two methods at least. Okay. Now MPPT controller means you have to have some arrangements of DSP kit or DSP to microcontroller, which will sense the voltage and controller voltage and current at the output of the PV array and do the calculation, and finally gives the reference. So for that purpose, this MPPT controller term is used. Okay. Now, before we discuss about that algorithm of MPPT, I want to mention something. Now, if this load, we are choosing one resistive load, and if this load is directly, and by the way, I would like to say that if you are having any confusion, you can stop me and you can have discussion as well. Okay. So if this load resistance is connected to this PV panel directly, so is it possible to operate this load resistance as maximum power point? It is possible in only one condition. Only one condition is there. You cannot change this load resistance to be operated at maximum power point. Suppose this PV panel is having this characteristic, this current voltage characteristic. Okay. And if this RL is varied, so RL is equal to 3 omega, RL is equal to 8 omega, RL is equal to 4.9 omega. Three resistance values are there. Okay. Now, according to this characteristic, we can see that this VMPP and IMPP is equal to 17.5 volts and 3.6 ampere respectively. We can see by this characteristic. Okay. Now, VMPP by IMPP is equal to 4.9 approximately. Okay. Now, the characteristic of this PV panel must match the characteristic of this resistance. Then only we have to satisfy the basic electrical fundament. Then only that operating point will be met. Okay. So for 3 omega characteristic, the operating point will be this. For 8 omega characteristic, the operating point will be this. And for load equal to 4.9 omega, the operating point will be this. So for load resistance equal to 4.9 omega only, MPP operation is possible. Maximum power point operation is possible for this PV panel for particular radiance and particular solar temperature, cell temperature, or particular environmental condition. Okay, there is only one operating point. We cannot have any MPP operation for any other resistive load, or we cannot have MPP operation for 4.9 omega resistive load for any other environmental condition. Okay. So to operate any RL at a maximum power point, we have to have some power processing unit in between the load and the PV panel like this. Okay. Load, PV array, in between one power converter is connected. It may be DC to DC buck or boost converter according to our own application. We are considering
Excuse
DC
me,
load
sir.
only. Yes.
Sorry for interruption. We are unable to see your screen.
You're not?
We are unable to see your
Are you sure?
screen. Since past
For
10
how?
minutes, since past minutes, we are unable to see your screen.
No, but I have shared it. My
In
God,
No, sir, it's not a shared one.
in search screen, it is visible. Pin the screen
Yeah, we have
by
pinned, but
search name.
No, what is? I have already shared it. Just a minute. Let me again share. I'm stopping it. Let me share again. I have already shared entire screen. Yes. Is it seen? Is it okay?
yes, sir. Now we are able
Yes,
to
sir.
see.
Yes, sir. Okay.
Okay.
Or
Yes, sir. Now it's visible. Thank you, sir.
so everyone was not able to see for
Yes,
past
sir.
10
Past
minutes.
10 to 15 minutes, we are unable to see.
My God.
No, sir. We can see.
Okay, few they are able to see, but for others, unable to see.
Okay, few were able to see.
Yeah.
Few were able to see now. Okay, so I'm just running the slide so that you can have the idea. Okay, this is PV array. This is the characteristic, solar characteristic, one maximum of power point. This PV array under partial shaded condition. Okay, this is schematic of partial shaded condition. So one point you have to remember that in partial shaded condition, there will be multiple peaks. There will be two local peak and one global peak. So we have to search for this global peak. Okay, so this is the system. actual PV system, I'm using that grid connected PV system here because MPP operation is, it is possible to operate the PV array always at MPP if it is grid connected. If it is in standalone mode, it will depend upon the requirement of the power, because the power required will be power produced. So you cannot produce the PV array power for maximum power operation and just feed it to somewhere. Okay. So there are. So is it visible? Again, I'm asking. Is it okay? Everyone
Yes,
is.
sir, it
Yes,
is
visible.
visible.
Yes, sir. Okay. Okay.
So two-stage system, single-stage system, we have already discussed that single-stage system, their losses are reduced because two-stage system, two power electronic converter stages are there. So we are focusing on MPPT controller here. MPPT controller is working continuously to sense this current and voltage at the output of PV array, okay, accordingly, and do some calculation according to the algorithm and give reference to the converter. If it is DC to DC converter, the reference will be duty cycle, and if it is to AC converter, the reference will be simple voltage reference to the voltage controller, and it will fix this voltage equal to the reference given by this MPPT controller. That's it. Okay. So the simple theorem is simple algorithm of P and O incremental conductance. We should have the idea of these are very simple basic theorems. So we must have the idea about these two at least for understanding the PSO based MPPT. Now, MPPT controller, this term is coming because we have to have some hardware, that is CDSP controller kit, to implement that algorithm which will be sensing that voltage and current and give that reference to that converter. So for that purpose, this controller term is used. Okay, so we have discussed that if the load is directly connected to PV array, it is not possible always to operate the PV array at maximum power point because these two are having their own characteristic. PV array is having its own characteristic like this IV characteristic, and this resistance will be having its own characteristic. For R is equal to 3, this characteristic. For RL is equal to 8, this characteristic. For RL is equal to 4.9, this characteristic. So the operating point will be the cutting point of these two characteristic of this PV array and characteristic of the resistance. Okay, so for RL is equal to 4.9 omega only, the MPP operation is possible, because MPP operation will be possible when VPV will be equal to VMPP, IPV will be equal to IMPP. So VMPP divided by IMPP here in this case is equal to 4.9. So RL is equal to 4.9 only will make possible this PV panel operate at maximum power point. So to operate any load at maximum power point, we have to have one power electronic converter, power processor unit, power processing unit in between like this. Okay, so this is load PV array, in between one power processing unit is there. So we are using this. For example, we are using only DC load. So DC to DC buck or boost converter is used according to our application. So DC to DC buck converter is very simple buck converter, very simplest converter. So I'm just within 1 to 2 minutes, I'm just explaining how the maximum power point is possible for different type of loads. So for buck converter, actually for buck, again I'm repeating that for MPP operation, this VPV divided by IPV should be equal to VMPP IMPP. If I'm considering the same characteristic, this previous characteristic, so this VPV by IPV should be equal to 4.9 for maximum power point operation. Now for buck converter, V output by V input. V output by V input is equal to D, where D is the duty ratio of the converter. There is a duty cycle, duty ratio in the converter. You have to switch on and switch off. Okay, that will decide the duty ratio. Everybody is familiar with that duty ratio, I think so. So D is equal to VL by VPV. Here in the case VL by VP, V output is VL, V PV is equal to V input. Okay. Now by having that power balance relationship, IPV VPV multiplication is equal to VL IL multiplication. These two powers will be equal if we are neglecting the losses in this converter. So by this power balance equation, we are having VIPV is equal to D multiplied by IL. Very simple. Okay. Now VPV by IPV, the ratio of output of that PV array voltage and PV array current will be equal to VL by IL multiplied by D square, which is equal to R load multiplied by D square. So this ratio can be represented in terms of this R load, external load, multiplied by the duty ratio. Okay. So for any load, for different loads, the different values of these loads, by adjusting this D, we can have this ratio VPV by IPV equal to 4.9, that is equal to VMPP by IMPP. So maximum power point operation is possible if we are using some power converter. Okay. So for boost converter, the same logic is valid. Okay. Now come to the basic of this part P&O and INC. I think one slide will be there. So P&O means perturb and observe. Very simple. The two terms perturb and observes are there. Okay. Something is to be perturbed and something is to be observed to track the maximum power point. ये maximum power point है. Okay. So perturbing means giving disturbance. So voltage is disturbed. So increment or decrement in the voltage is given. Okay. And what to be observed? The power is to be observed. So if increment in the voltage is given in any direction, perturbation is in voltage is given in any direction, and if power is increased, so the direction of perturbation is continued. Otherwise, direction of that perturbation is reversed. So there should be some initial point. जब भी हम कभी MPP search करते हैं, तो there will be some initial point. So suppose this is initial point. Okay. Now if decrement is there, delta VPV. So power is being compared. So this power is less than this power. So power is decreased. So direction of perturbation is to be reversed. So now the voltage is to be incremented. So voltage is incremented, power is increased. Again, voltage is to be incremented, power is increased, and keep on, and so on. So it will reach this maximum power point. And again, when the voltage is being incremented, the power is decreased here at this point. So what to do? It will be reversed. The disturbance perturbation should be reversed. So voltage is to be decremented. So power is increased. Again, power is increased. That means decrement should be continued. So it is decremented. Then power is again decreased. Then the perturbation, the direction of perturbation is again reversed. So finally, what will happen? It will oscillate at this point, MPP point. Okay, it will not be fixed at this point, and that oscillation will be depending upon the step change of voltage to be given. Okay, so there is problem with that P&O, that is oscillation in steady state. And another simple method, another basic method which we have mentioned, that is INC, that is incremental conductance, that is also have oscillation. It will not reduce, it will not remove that oscillation at a steady state condition. Now another problem is it will fail. The P&O method will fail in fast changing environmental condition. Okay, why it will fail? We can see here. Suppose this is the characteristic for some irradiance. Okay, and this is maximum power point. Point thoda sa miss ho gaya idhar. This is maximum power point. Now suddenly the irradiance is increased, and the new characters we are getting this one. Now power, the voltage is incremented. So increment to the voltage is given. Now power should be decreased, but power is being increased because this power is to be compared with this power. Now incrementing power is increasing the power. So this increment will be continued. So this operating point will not be moving to this point. This operating point will be moving to this point. Okay. So there is a problem in searching MPP if the fast changing environmental condition is there. Now incremental conductance MPPT method be able even if the fast changing environmental condition is there, because this INC method is based on the slope of this curve. If slope is positive, increment should be there. Slope is negative, decrement should be there. That is there. So it is based on the slope. So slope is 0 at MPP. That means dp by dv is equal to 0. Slope is positive at left side, that is dp by dv is greater than 0. Slope is negative at right side, that is dp by dv, which is less than 0. Now, why it is called incremental condition? Conductance. The power is, the slope of power is there, and we are using this term. Okay. Some reason must be there when we are doing some nomenclature. So incremental conductance would be there. Actually, the MPP is tracked by comparing instantaneous conductance to the incremental conductance. How? Because this dp by dv can be expressed as d by dv. P is equal to v multiplied by I. So dp by dv is equal to v into di by dv plus I. Now, at MPP, this part dp by dv is equal to 0. So this part is equal to 0. So we can say that di by dv is equal to minus I by v. So what we are comparing? We are comparing incremental in instantaneous conductance with incremental conductance. That's why this method is known as incremental conductance method. And by the way, actually we are sensing current and voltage. Okay. So here we are just having this, using this current and voltage, and we are just comparing this. We are not calculating the power again and again. Okay, we are not comparing the power and again comparing with the previous value. We are using only voltage and current and difference of voltage and current. So this DI will be calculated by using the present current and the previous current. That previous current is to be stored. That is why we need that TSP controller kit or MPPT controller. So di by dv should be greater than I minus I by v for the left side, and di by dv should be less than minus I by v at the right side of MPP. So increment and decrement of the voltage should be given accordingly, and finally it will settle at MPP. Okay. So this was about the MPP condition or MPP tracking for uniform irradiance. Okay, now what will happen if the partial shaded condition is there? So in partial shaded condition, there are multiple peaks, say pattern 1 and pattern 2. So in these two cases, both P&O and INC method will fail. Okay, and they will stick to some local MPP. Suppose we start from these here at this point. Okay, so in both the pattern, it will reach to these two local points and it will stick. It will not be able to search this point, okay, or this point. Is it? Suppose the initial point is here, so it will stick to this point. Okay, it will not reach to this point. So both P&O and INC method will fail in such type of condition. And actually, there are many methods which has been used actually, which has been by modifying these basic P&O method and INC method. Many methods has been published in research papers as well to find out the global maximum power point. But actually, they are having some limitations. In some conditions, they fail. Okay, or they are complex, or they are not. They are not very fast. They are. Hello. Someone is there. Okay. Okay. So there are many methods which has been published for searching the global MPP by modifying, by using these two P&O and INC method, because these two are simple method. So, but there are some limitations in all those methods. Some methods are very complex, some methods are slow, and some methods are fails in different types of some particular environmental condition. So they are not able to search all type of partially shaded MPP in all type of partially shaded conditions. So Now the PSO, particle swarm optimization, that AI, evolutionary algorithm or artificial intelligence, it's yes. Some question. Someone has. There is some disturbance here. Okay. So the PSO, particle swarm optimization, and why particle swarm optimization? PSO. Actually, when we are providing some solution to any problem, so there are many points, there are many conditions which is to be satisfied. It should be simple. Okay, it should be simple to use. It should be fast. It should be economical. Many things are there. So many evolutionary algorithm AI techniques are there which can be used. Like ANN has also been used. Okay, but this, because of the simple structure of this PSO, we are proposing, or we are discussing the PSO based MPPT controller. Okay, so partial shaded condition में क्या है कि many local MPPs are present. So common MPPT methods fail to reach global peak. So evolutionary algorithm or PSO based algorithm may give the solution. So it is simple solution and it gives accurate solution and very fast. And again, I'm telling it's very simple and cost effective because of the simplicity. Actually, when particle swarm optimization, this term is used in power system. So there are many applications in power system of particle swarm optimization, like optimization, optimal location of that distributed energy resources, or unit commitment in scheduling of generator. Different applications of particle swarm optimization they are there. So many iterations are there, so many agents or particles are there in those applications that a question will be there ki, how it will be simple. So regarding MPPT, I will come to that point how this is very simple in MPPT. That's why we are using this PSO based MPPT controller. Now, what is particle swarm optimization? So different optimization techniques are there, and those are basically inspired by the nature. So this optimization technique, the PSO, is also inspired by the natural phenomena or nature. It is inspired by, based on bird flocking behavior. The particle, a simple particle, swarm means a group or cluster. So flock means again the bird, cluster of the bird. So it is inspired by the group or flock of the bird behavior in search of some food. Okay, and it was proposed way back in 1995 by James Kennedy and Mr. Russell. Now these birds moves around in the search space looking for the food. Food is the best solution, final solution, and particle is a member of that swarm, member of that flock, member of that group, that is birds. So based on this behavior that birds are searching for foods, and finally they reach to a single solution, the particle swarm optimization has come into picture. Okay, so what what is the process? Actually, number of agents are used, number of agents that constitute a swarm moving around in the search space looking for the best solution. So number of birds are there. Okay, they move around in the search space for best solution, that is food. Now each particle in search space adjusts its flying. Each bird in the group in the search space adjusts its flying according to what? According to their own experience as well as the experience of the other birds. Okay, the individual birds are having the senses where we can have that food, that solution, the tendency to find the solution. And by combining the self-experience of individual bird and the group, the social experience, the overall movement is there, and finally they reach to a single solution. Okay, so this is the basic idea of the bird flocking behavior, and based on this behavior, particle swarm optimization technique has been developed. So we can say that each particle, so each particle means each agent member of that group. Each particle behaves according to the two simple rules. it will move towards the best solution by the particle itself according to its own experience. Every particle will have its own experience. So it will move towards the movement for the individual particle will be based on the best solution by its own experience, that is P best. And the movement of individual particle will be also based on the best solution of the entire population, the entire group. That is the global best position, G best. Okay, so there are actually 2-3 points in PSO parameters. One is position, another is velocity. Okay, position, velocity. Okay, so these two are the main parameter, and according to the P best and G best experience of the individual and experience of the whole group, the velocity is decided, and according to the velocity, the position is changed. The velocity is basically the step size in the change in the position, and the position is changed. Okay. So this is expressed by the following these two equations. Okay, these two equations. These equations are velocity. This k is instant. K is instant. So previous instant is k, and k plus 1 is the next instant. K plus 1 instant, and previous instant is k. Okay, so the position at kth instant is Sik. Now the new position Sik plus 1 will be decided by the velocity. ठीक है, the step change. Now कितना change हमको करना है, how much change is possible, how much change is being done to this will be decided by the best position of the individual particle I and the global best position of the entire group. Okay, so this is the position, previous position at kth instant. So best position minus the previous position will be deciding factor for the step change, and again the global best position minus the difference between the global best position and the kth instant position will be again deciding factor for this step size change in the velocity, step size change in the position, that is velocity. Okay, and this lambda ik is the previous velocity. So previous velocity, individual best position of ith particle, global best position for the entire group will decide the new velocity. Okay, and new velocity is added to the previous position, and new position is obtained. Okay, and these are different factors which will be using. The k is iteration number, obviously instant. W is inertia weight, that is factor for this previous velocity. R1, C1 are the random variables. C1, C2 are the acceleration coefficient for best position, individual best position, and global best position. And in this way, this whole particle optimization is defined by the expression. Okay. Now, for how long this process is being continued? Step change is given to the position. So how it is being changed? Now there should be some objective function. So that objective function is to be satisfied. So that objective function is, say, f, which is known as fitness value evaluation function. That will depend upon this Sik. So f function of Sik, this is position. Again, I'm telling this is position, instant position, that the present position. So if Sik is greater than the function of the best position of I, it is greater. If it is greater, then particle position is to be adjusted. Okay. Now, if it is not greater than the P best position, then the particle position will be simply P best I. I don't know whether you're appreciating or not, but I'm trying. Now this is the trajectory showing the PSO moment of particle. So Sk is the present position, Sk minus 1 is the previous position, lambda Ik is the present velocity. So present velocity, this difference, or P best or G best, these three factors will be having the role in the movement of this particle Sik to Sik plus 1. Okay, so lambda Ik multiplied by W is this one, this factor, this one. Then G best minus Sik multiplied by the factor, this factor C2R2 is this one. Okay, then P best I minus Sik multiplied by this factor is represented by this line. So by summation of these three lines, we are getting this new position, and it will be continued till this fitness value evaluation function is satisfied. Okay, now come for MPPT, PSO for MPPT. For MPPT problem, we have understand the basic equations of PSO, that we should have that position, we should have velocity, and we should have objective function. Now in MPP, maximum power point tracking, we have that characteristic, if you remember, and we are having the voltages, PV voltages, we are having the powers corresponding to the PV voltages. Okay, so here position of the particle is SI. SI is equal to VPV. So PSO particle position SI here in MPPT case is the PV array voltages. So I is the ith particle. So if number of particles are there, so number of PV voltages would be there according to the number of particles. So if n number of particles are there, so n number of positions will be there, S1, S2, S3, S5, S4, Sn. So there will be n number of VPV will be there. Okay. Now the objective, so we can represent by this equation SI, the particle positions are VPV1, VPV2, VPV3, VPVn for n number of particles. If n number of particles are chosen for PSO based MPPT, there will be n number of position, n number of PV array voltage. Now objective function will be obviously PV array power. Okay, so if PV array power for ith particle, consider ith particle. Suppose ith particle is second particle. Okay, so for second particle, second voltage, second particle position means second voltage PV array voltage. For that PV array voltage at kth instant, present instant, the corresponding PV array power is more than the previous position of this VPVI, okay, previous position of the VPVI. Then what is needed? That means we are getting more power if we are changing the particle position. That means it is to be adjusted. The particle position is to be adjusted. Now, if it is not more than that, if it is less than this, that means the particle position to be fixed as previous particle position, this VPVI k minus 1. Clear? Okay. Now come to the actual problem, actual case. So number of particles, it's very important actually, number of particles in PSO. So I have started actually, I will show the simulation results, some simulation results, basic simulation results. I will start it with number of particles equal to 11 number of particles. So number of particles are increased, that means number of complications are increased. For each particles you have to calculate and you have to find out the P best and we have to find out the G best of the all particles and do the calculations, calculate the velocity for individual particles again and again for using that formula. So I started with 11 particles, reduced number of particles, and finally, when 3 particles are used, we are getting the same result actually, and with very fast speed, because if number of particles are increased, so calculation time for each particle is to be given for individual particles. So the sum of the calculation time of each particle will be uh, very high, if the number of particles are increased. So MPP tracking will be very slow. So the purpose will not be solved. So the bare minimum 3 particles, bare minimum 3 particles. You cannot choose more less than 3. Okay, so bare minimum 3 particles are able to give the solution to find out the maximum power point very easily, very effectively. Okay, and very fast. So I've chosen this n number. So that's why the simplicity of the PSO regarding MPPT is justified. So I have mentioned that when we are thinking about PSO in power system, so huge system is there, multi-dimensional objective function is there. So number of particles are there, so many iterations are there. So how come it is simple? So simplicity lies in the number of particles. Only 3 particles are there, and this is only not multi-dimensional problem, only 2-dimensional, only 2 power and voltage is there, for single characteristic is there. Okay, now the process कैसे बढ़ेंगे इसको, process is there. What is the process, basic process? So first we initialize the position and velocity as well. Initialize the position. So 3 particles are there. So 3 positions will be there. Positions means the PV array voltage, VPV1, VPV2, and VPV3. Okay, how this is chosen? There will be some basis on that. So this 3 particles initialization is done so that it will give the possibility of the searching of the full area of that characteristic. Is it? Full area, the whole area, the maximum area of that characteristic voltage PV characteristics should be searched out. Okay, so for that purpose, we are using one rule, and it is quite it is giving quite the good result, satisfactory result. 60%, 80%, and 85% of VOC of PV characteristic. Okay, if initialization is done as 60%, 80%, and 85% of VOC of PV characteristic, it will be able to search all type of MPP in any type of environmental condition. So this is for initialization of position and velocity. Initial velocity can be decided by the wisdom of user. So it will depend upon many factors. That is what is the maximum voltage, or what is the open circuit voltage of your system, what is the rating of your system. According to that, according to the voltage, maximum voltage or open circuit voltage of your PV array, the initial velocity is decided by the wisdom of the users. Okay, now I'm showing the tracking of that maximum power point by the PSO. So here 3 particles are chosen. This one, particle number 1, particle number 2, and particle number 3. Okay, 3 particles are there. Now initialization is given as 60%. This voltage is 60% of this VOC. This is 80% of this VOC. This is 85% of this VOC. Initial. So what is the P best initial? It will be obviously 60% of this voltage, 80% of this VOC, 85% of this VOC. Initial velocity is given, some initial velocity is given, and according to that initial velocity, again this formula is there. So because 3 particles are there, so 3 times calculation will be done. 3 times calculation will be done and calculation times for 3 particles will be sum up, and this will be one PSO. This will be one PSO step time. This will be one PSO step time. One PSO step time is the time of calculation by one particle multiplied by 3. Okay. So this formula is used to find out the new velocity, and particle will move accordingly. New particle position for these 3 particles will be there. For example, this particle, new particle position will be this one. For this new particle position will be this one. For this new particle position will be this one. Okay. And this will keep on repeating, and finally it will settle to single solution, where the position for all the 3 particles P best will be same, and the global best position will be equal to the P best of the all 3 particles, almost equal. I'm not telling that they will be completely equal. There will slight difference will be there, but they're almost equal. So if they're almost equal, then that means there will be no oscillation at this point. Negligible, completely negligible oscillation at this point, because all the 3 particles will be having same solution. Okay, so this is for uniform irradiance, and this is for your partial shaded condition. So in partial shaded condition as well, these 3 particles, the initial positions are this one, and this one, and movement will be like this. The first movement of this particle is this one, okay, and the first movement is this one, and this power is compared with this one. Okay, so this power is more than this one, so movement will be further in the same direction. So all the 3 particles will be moving towards the global best position, and this global maximum power point is searched out. And because G best means this voltage will be equal to the P best of the all 3 particles, so there will be again almost negligible oscillation at steady state will be there, which was not there in the case of PNO and INC. Okay, so looking very simple that PSO हमने use किया, and simply we are just having the solution. Very simple solution. There is no problem at all. But it's not actually true. There will be some small or large problem will be there if we are having some solution, some side. If you are getting some medicine, it will be having some side effects. So there is some problem or one basic problem which was identified when PSO was being used. We want to discuss that problem. Very simple problem, very small problem was there, and very simple solution was there. So if irradiance increases, suppose uniform irradiance is there, okay, and if irradiance is suddenly changed, and if irradiance increases from the low value to high value, or temperature decreases. So if temperature is decreased, if you remember that PV characteristic, if temperature is decreased, actually the power is increased, and if irradiance is increased, then power is increased. The effect of temperature in irradiance on power is opposite. Increase in irradiance increases the power, and decrease in temperature increases the power. So if all of a sudden irradiance is increased, say for example, then simple PSO which we have discussed will be able to successfully track the MPP. Why? Because irradiance is increased, the new power is compared with the previous power. Okay, objective function is power. New power is compared with the previous power. So new power is more than the previous power. So obviously the position according to the new power will be the P best of individual particle. So the previous characteristic is just removed, and the search will be continued on the new characteristic. But if irradiance is all of a sudden irradiance is decreased, or temperature is increased, so the new characteristic this one. New characteristic will be this one. This is the previous characteristic, and all of a sudden irradiance is decreased. So this new characteristic is there. Okay, then what will happen? There will be some problem, and normal PSO is not able to track the new MPP position. It will resettle to the previous MPP position. There is solution. The solution is written here in the third line, but before that I would like to discuss that problem. So this is the previous irradiance. The three particles are settled on this MPP. Three particles are settled. That means position of the three particles is VMPP old. ये VMPP old है. Now all of a sudden irradiance is decreased. So position is there. So what we do actually, irradiance is changed. If irradiance is changed, one point is to be introduced in PSO, that if irradiance is changed, the initialization, there should be some reinitialization of the particles. There should be some reinitialization of the particle. Always. Why? Because if reinitialization of the particle is not there, it will be sticking to this one only. Because power will be compared, obviously. Okay. So reinitialization is done. So reinitialization is done. So three particles are there. One particle is kept at the previous position, and the two particles are reinitialization. It is decremented. First particle and third particle is incremented. Now what happens here in this figure, the whole process is shown actually. At this instant, the irradiance is decreased. So all of a sudden, this whole power will be decreased. Now the power for these 3 points, reinitialization is done after the irradiance occur, and the 3 particles are there, 3 new positions are there for the 3 particles. Now the power is compared with the previous power, and obviously the previous power will be more than the new power. It is but obvious that previous power will be more than the new power. So the P best of individual particle, the P best solution of the individual particle will be according to this previous power, that is VMPP old. Even if we have adjusted this point, the position of this is changed, position of this is changed, the position of this is not changed. Even if this is done, but the power is compared with this one, so previous power is more. So what will happen? The P best of these 3 particles will be this voltage position, that is VMPP old. And it will always be like that, because this power will be always more than these powers. So finally what will happen? The voltage, all the particles will be settled to the same value, that is VMPP old, this one. And power will be corresponding to this VMPP old, power will be corresponding to this one. This power will be this one. Okay, this is the problem. So what may be the solution? So there should be solution. So if we are giving the general method, so there should be some very simple solution should be there. The very simple solution was there, this third line. The solution of this problem is modified PSO method by giving one PSO time step delay after the point of environmental change and reinitialization of the particle position. Okay, velocity and P best. What to do? Very simple. One delay of one PSO time step is done. So this delay is provided. So that it is settled to this one. It is settled to this one. Then reinitialization is done. Before that, reinitialization is not done. So we are providing simple delay. After then reinitialization is done, then the new power, this power is compared with this power is compared with this one. Obviously, this power is not compared with the previous one. The power is compared with these 3 powers. So obviously, the search will be according to this new characteristic. The previous characteristic actually is removed from the process, is removed from the picture by giving simple delay of 1 PSO time step. Again, I am telling that 1 PSO time step is the sum of the time of the calculation time given to each particle. Here 3 particles are there. So the time given for the calculation of one particle multiplied by 3 is 1 PSO time step. So delay is given 1 PSO time step. After then reinitialization is given, and then the same process is repeated, and finally these 3 particles, the position of these 3 particles will be settled on this VMPP new, this one, which is less than this VMPP old. This VMPP new is less than VMPP old. This VMPP new is less than VMPP old, and this PMPP new is more than this power. So this is the solution. So we are getting a simple general solution of PSO based MPPT tracking, which can be used, and it is able to track almost all type of environmental conduction, complex, you can even very complex partially shaded condition, and I myself have checked it, and it is able to search, and it's very fast as compared to the other methods. So I'm showing the case study. This is one grid connected system which we are taken for testing this PSO, simple general PSO based based MPPT. 375 kilowatt PV arrays considered, and it is connected to this utility grid with the help of this 3-phase 2-level voltage source inverter, single stage. Then this is filter. Then transformer is needed because we have used that utility grade equal to that 12.6 medium distribution grid, 12.6 kV medium distribution grid. So transformer was needed. This is very high power rating of PV array. Now the parameters of this 375 kilowatt PV unit parameters are like that. And this 375 kilowatt PV array is made of by using this 150 watt PV cell. Okay, so the rating of this PV cell was like 150 watt. 150 watt PV cell means, ये 150 watt का क्या मतलब है? That means this cell will produce 150 watt maximum power produced by this 150 watt PV cell at standard test condition, that is irradiance equal to 1000 watt per meter square and so cell temperature equal to 25 degrees centigrade. Okay, so VMPP at which maximum power is occurred is 34 volt. IMPP is 4.54 ampere. Open circuit voltage is this one. Short circuit current is this one. So how can we formulate this 375 kilowatt with the help of 155 watt solar cell? So 25 such, this is not solar cell, this is wrongly written. This is 150 watt. This cell is wrongly written. This is module actually, 150 watt module. Cell is very small actually. So by using this 150 watt PV module, 25 such type of module is connected in series to make a string. Okay, so voltage 25 multiplied by this, 25 multiplied by this, they are connected in series to form a string, is equal to 850 volt. Okay, 25 multiplied by this is equal to 1085. So 25 such type of modules are used to formulate a string, and 100 such strings are connected in parallel to formulate finally 375 kilowatt array. So 100 means the 4.4 ampere parallel connection means current will be added. So 100 strings are connected in parallel. So 100 multiplied by 4.4, that is 440 ampere is the IMPP of this formulated 375 kilowatt PV array. Okay, now parameter of PSO is calculated. So this is the process we have to do. before the real implementation of PSO in the real PV system. So we have to calculate that inertia weight, the parameters that C1, C2, R1, R2, etc. So how these are calculated? Actually, these are calculated by using iterative process for in MATLAB programming. Iterative process where we start that C1, C2 at some place and we go on increasing that C1, C2 and find out the solution. So this is actually, this process is this process prior to implementation of the PSO in real time. This process will take time because the many iterative processes there to find out the single solution, but only 3 particles are there, so this is not that much cumbersome. Okay, this is again that the process itself is simpler as compared to the other PSO process. For example, this inertia weight W, finally inertia weight was selected as 0.4. Now, how it was selected? It was started from 0.9 and decrement given to this inertia weight was 0.02, and started the whole process and find out the sampling time and find out the total solution, how much time the solution converges, how much iteration it is taking. So ultimately, the solution converges in minimum iteration of 0.4. So it is finalized to be 0.4. Okay. Now come to the PSO time step. The actual value of PSO time step in this case study. So MPPT sampling time was given to 0.02 second. So this 0.02 second is given to all the 3 particles. 0.02 second for one particle. Okay. So what that one particle 1 will done within this 0.02 second. It will do all the calculation. It will do all the calculation. The position is decided. New position of that particle 1 is decided. Position means the voltage reference is decided. Okay, the whole system will settle on that particular voltage of PV array. Okay, power is calculated. All these calculations should be done within these 0.02 seconds. So this is MPPT sampling time, because according to that position of particle 1, according to that voltage reference of particle 1, whole MPPT process, whole settlement of voltage of PV array should be done. Okay. Then after 0.02 second, the next particle come into picture. 0.02 second will be given to that. Then after 0.02 second, the third particle will come into picture. So total time is 0.06 second. And this is called one iteration. And now the MPP is successfully tracked within simple 10 iteration. Simple 10 iteration. 10 multiplied by 0.06 is 0.6 second. Okay. So it's very fast. Now some simulation results I'm going to show. So this was for uniform irradiance we have considered. And suppose irradiance is increased. So first irradiance was 500 kilowatt per meter square with cell temperature 25 degrees centigrade. Now irradiance is increased equal to 800 kilowatt per meter square with temperature 15. So new characteristic is this one. So VMPP previous was 831 volt with 175 kilowatt, and new VMPP is 880 volt and with 315 kilowatt. So if we are comparing the actually I'm sorry to say that, yes, this hill climbing is written here, and hill climbing HC, don't be confused with this HC. HC is hill climbing method. Hill climbing is another name of that P&O. Okay, so this, consider this red one to be P&O method. Okay, and PSO is this one, the simple which we are discussing. Now initial voltage reference was 650 volt. Here it is settled. Now at this point MPPT controller is enabled. Now this HC or P and O, the conventional method, will again start. and it will track, and it will be able to track MPP and reach the final value at this 1.1 second. Okay, so total 1 second is there, almost zero point 0.8 to 1 second is there for searching this P&O method with same time step. Same time step means 0.6 time step is given. Now PSO method with PSO method started from here and it is tracked here. 0.4 second, 0.4 to 0.5 second, almost half time. Within half time, it is searched with PSO method, and moreover, it is almost having negligible oscillation. And what is happening with HC or P&O? It is having the oscillation. So this is for 500 watt per meter square for this maximum power point. Voltage is 831. Voltage is 831. Now at this point, irradiance is changed and new characteristic, this characteristic comes into picture. Now BMPP new is 880 volt. So again, this actually continuous searching is going on. So PSO is again able to track this within this second, and HC is tracking this second, and oscillation with P&O is there, and negligible oscillation is there with PSO with fast tracking. Come to partial shaded condition, another case. This is one schematic of that PV array is shown. Like this is having, these white part is having full irradiance, and this is having full irradiance means 100,000 watt per meter square, and these portion are having 600 watt per meter square. This portion 500. Again, this darkest is 400, and the characteristic, power characteristic of the PV array which we are getting is this one. Okay, so there are two peaks. This one is the global peak with VMPP is equal to 895. This is one local peak. Adjacent local peak voltage is equal to 720 volt. Power is 241. Here power is 251. Almost 10 kilowatt difference. Almost 10 kilowatt difference. Voltage is 895 global peak. Voltage is 720 volt local peak. Difference in power is almost 10 kilowatt. Now compare. Okay. So at this point, initial reference is given equal to 650. At this point, MPPT is enabled. Now with INC, the better one, the better conventional method, INC, incremental conductance method, better conventional method. Both are searching. Okay, both are searching. And actually INC is delayed, this voltage. It is searching, but very delayed. The searching time is too large as compared to this one. And moreover, it is sticking to voltage equal to 720 volt. This is local peak, not the global peak. Local peak, which is 720 volt, global peak is 895. So 895 is the global peak. PSO is searching. It is also started at 650 volt. It is also started at somewhere at this point, 650, this point. Okay, so finally it is sticking to 720 volt and it is reaching to 895. And you know, the power difference is 10 kilowatt, and if it is continuous, then so much energy will be lost. And obviously voltage oscillation will be there at MPP. Another case is there. When irradiance pattern changing from uniform to partial shaded condition. The previous case was initial condition was not there. Initially it was 650 volt. But here in this case, initially uniform irradiance was there, and all of a sudden partial shaded condition comes into picture. Okay, so this partial shaded condition comes into picture, but previous to this partial shaded condition comes into picture, there was a uniform irradiance. Okay, now this partial shaded condition will be having two peaks are there. This is actually global peak, very close to each other. The global peak is 729 volt. The difference in voltage is very high. Just see, 792 voltage. This is local peak, 864 volt. So why this is local peak? Because the power is 198, which is less than 202 kilowatt. The power difference is small, but the voltage difference is too large. Okay, but this one is global peak. So to operate at maximum power point, the maximum power point tracker should track and reaches to this position. Okay. Now, previous condition was that there was uniform irradiance of 1000 watt per meter square, standard test condition, and voltage, maximum power point voltage was 850 volt, settled. It was already settled. Incremental conductance, red one, blue one is PSO method. Both are compared. Already settled at t is equal to 1.6. Irradiance is changed, and new partial shear rate condition comes into picture. So both will try to track. So 850 volt, 850 volt. Both will start from 850 volt. Okay. So from 850 volt here, 850 volt here, the INC will reach to this 729. Here, INC will reach to 729. I'm sorry. INC is red one. INC will reach to 864. Here 850. INC will reach to 864. It will stick to 864, which is local MPP. And that PSO starting from 850, it will be settling to the global peak, which is 729 volt. Both will start from 850, but PSO, according to PSO, it will settle to the global peak, and the ILC will be settled to that local peak. Okay. So there is a comparison of PSO-based MPPT method and other methods like speed with uniform radiance. PNDO method is slow, INC is again slow, PSO is very fast. Rather, I should have written very fast. Now, partial shear rate condition tracking, PNDO not possible, INC not possible, and PSO always. Tracking speed not applicable for PSO, and here in PSO method, actually, if we compare this PSO method with other methods, which is based on conventional method to find out that to track that global MPP, even with that also, this is fastest. And complexity wise, the PNDO method is very simple. Actually, it is simple. It is very simple. And PSO method is also simple. It is not as simple as this PN2, but this is not very complex because of the three particles. So it is very feasible. Actually, we can very easily use it on that normal cheap DSP controller kit for practical application even. So these are the advantages. So modified MPPT method is simple to implement, gives accurate and fast tracking. It is suitable to track MPPT in even complex change condition. Oscillation almost zero. So we have already checked it for different types of complicated partial shear rate condition. So it is suited for all where other methods fail. And structure wise, it is very simple. So it can be used with low cost digital signal processor controller. So it provides a MPPT solution with cheap, reliable and fast, cost effective economic solution for MPPT working in any type of PV array, PV system, whether it is two-stage or single-stage, standalone or grid-connected mode. Thank you. So, any question?
Hello, sir. I'm Jesh from Textile and Engineering Institute. Sir, you said that you used a modified PSO in order to overcome two problems.
Yeah.
But what modification in the equation for velocity and position, sir, accordingly?
It was reinitialization. I have told that whenever irradiance is changed, see, there's a continuous process. The three particles are settled on MPP. Is it? Now,
Okay.
in the algorithm, this part is inevitable. Whenever irradiance or sudden change is there, so you have to find out what the sudden change means. It's very easy actually in PV characteristic. If sudden change is there, okay, so there should be some logic with sudden change in irradiance. So if sudden change in irradiance is there, so reinitialization of that velocity, that P-based solution, that velocity and position both should be there
Okay. Okay.
always, whether it is uniform irradiance, whether it is partial shaded condition, always. But if that one case, because I'm discussing the general solution. If the irradiance is decreased, that case was actually the question mark, because irradiance can be increased, irradiation can be decreased. So there was question mark. What will happen? Even if irradiationalization is being done, it is not able to track the new MPP. It is sticking to that previous VMPP old. Huh? Because it is comparing to the previous stored power. So one delay is given.
Right.
Whenever irradiance comes, one delay equal to the PSO time step, that is 3 multiplied by the MPPT step,
Okay.
that is 0.06 here, for example. Okay, then it will not be then reinitialization of that, after giving that delay, reinitialization of that position and velocity is to be there, and it will be comparing the power according to the new characteristic. The previous characteristic we are just removing from the process by doing the simple delay. Okay, so very simple, you can say very simple complexity. Complexity word is not right actually. Very simple addition in logic is there. Simple delay, and we are getting the general solution.
Sir, how the initial values of voltage was obtained for three voltages, sir? VPV 1,
Yes,
2, 3.
yes, actually, these three voltages are to be decided so that it will be able to search the whole entire area. Is it? So, I mean, something is to be decided by the developer. So,
Okay.
what, according to my experience, I will tell you that, like, it was 60% of that VOC, 80% of that VOC, 85% of that VOC. If we are taking these three, actually, I have tested it on almost 34 types of partial shaded condition with high irradiance, 1000 irradiance, then 200 irradiance. You can see. So if we are considering these three values, 60% of, you can take 55% as well. 55%, but if you are that increasing the gap, obviously time will be more. So 60% was optimized actually, 65%, 60%, and 80%, 85% of VOC. If you are taking these three, you will be able to get the solution finally. It will be giving the whole search area. So if in the case of partial shaded condition, your question may be in the partial shaded condition, one peak may be below than 650, one peak may be below than the 60% of VOC. There may be the question in the partial shaded condition. There is one partial shaded condition in which one peak is below than that 60% of VOC. So in that case, what will happen? But if you go and check out the partial shaded condition and characteristic of different type of characteristic, you just change the irradiance of different modules, and so it is sure that that peak below 60% of that VOC will not be that global. It is 100% sure, 100% sure. So global peak will be in between that 60% of VOC and 85% of VOC in all type of condition, environmental condition. So that's why we have chosen that. And
Sir.
in this case, like one more point, initialization point you have asked. So this is for initialization of position. Now initialization of that velocity. So here in this case, the VOC was 1085. Okay, and I have written that sentence. It will be decided by the wisdom of that user or developer. So in my case, it was 4 volt only. That velocity, initial velocity was 4 volt. But initial velocity, actually, whatever be the initial velocity, if it is 5 volt, in the next step only, the velocity will be adjusted. In the next step only, you will be getting 4 volt will be converted into 50 volt. It is quite possible. Initially, 4 volt is given. In the next step only, by calculating the P best and G best of all the 3 particles, that velocity may change from 4 volt. The next step only may change. It will be from 4 volt to 20 volt, 25 volt. Is it?
Okay, sir. Sir, is there any performance measure for MPPT controller for your method, PSO, modified PSO method?
Performance measure is yes, the results which I have shown in the slides. Those are very few results I am showing. The performance measure means
How best?
the PSO is able to track. Yes.
Whether it is
Three parameters.
in all 100% of the cases.
Yes. Yes, possible. I mean, 34 cases.
Okay.
I mean, I'm not able to show it right now. All the cases. I have those cases actually.
Okay, sir.
I have all those cases. Actually, different questions came into mind, like that question key that peak may be below than 60%. That question was also there. But it's 100% sure in each and every type of partial shaded condition. I'm not talking about only there are, say, 100 modules are there. I'm not talking the case key 99 modules are just damaged or only one module is there. I'm talking about the partial shaded condition. Okay, all modules are working properly, but they are in shaded condition. Okay, so that peak is less than the global peak. It will not be global peak. It will be the local peak. So these type of conditions have been taken into account, and 35, 34, not 35, 34, yes, 34 conditions with different irradiance and different modules of this whole 375 kilowatt. That was possible to find out.
Thank you,
Track.
sir. Thank you.
And within 10 iteration, that was the beauty actually, within 10 iteration. Yes.
Any more questions from participants? Sir, we have one question in chat box.
Yes.
Which is the most suitable software for testing MPPT algorithms?
There are, which is the most suitable software for testing any software which in which you can simulate your system. That's it. Like MATLAB is very simple to use, user friendly. You can use MATLAB, even PSIM, any software on which you can simulate your system. So MATLAB is user friendly, so you can use MATLAB, and available everywhere. It is available everywhere, so you can use MATLAB.
Okay, one more question,
Actually,
sir.
PSCAT, MATLAB, PSIM, even PSCAT. PSCAT is actually more close to the real.
Yes.
More close the real property of different switches. Is it? So PSCAT is also suitable. But it will depend upon the software which you are comfortable with. If you haven't used PSCAT, so first you have to learn PSCAT. It's a general question actually. Okay.
Okay. Thank you very much, sir, for delivering an informative and wonderful talk on the PSO-based maximum power point tracking controller for PV solar system. Thank you very much, sir, for spare your valuable time for your busy schedule for this FDP. One thing I want to share with all the participants that in spite of his health, his ill health condition, the sir has come to take an online for this lecture, sir. Thank you once again, sir. Thank you.
So I tried because the condition is not well. I mean, I'm not well.
Yes, sir.
You
No,
have
no,
already
sir.
told. I didn't wanted to say it to the participant, but I tried. If any question is there, you can ask. So I think
It's
it's
already
thank
explained, sir. So
okay.
many questions, sir.
Thank you
Okay,
for
thank you so much, sir.
listening. Thank you for having the patience to listen to me carefully. Okay. So
Thank you,
some
sir.
questions are there. Some questions are still there. Is it? No. In chat
Sir,
box.
one question is how to PSO-M file interface with MATLAB Simulink in every iteration.
How to interface? Let me go to chat box.
Interface with MATLAB Simulink in every iterations.
Let me. Is there any? It is written on chat box, or you are? This is your own
Yes, sir.
question.
No, it is written on chat box.
How to PSOM file in how to PSOM file interface with MATLAB Simulink in every iteration. So that for that purpose, that you can write the program, and you can write the program. There is a provision to write the simple program and interface that program box to the MATLAB Simulink. So though both can be combined. So input to that program box, I'm talking in general term, I'm not talking in MATLAB. So in any software, the simulation platform is there. Okay. So in that simulation platform, you can combine a platform. The platform in all software is given where you can write your own program, where it is PSCAD, where it is MATLAB. Okay, so both can be interact, the programming interface and the Simulink interface. So in the programming interface, you can give the input V and I, instantaneous input V and I. Okay, and those two values can be used inside that programming interface, programming box. You have written program, those can be stored. Okay, present is present at present instant and previous instant, and do the calculation, and output of that box, that platform providing the programming will be what? It will be voltage reference to the voltage controller, or duty cycle reference to that DC to DC converter. According to that voltage reference duty cycle, the output voltage of PV array is settled. Okay, and by repeating this process again and again, comparing the power, etc., or by following the algorithm which you have used in your programming box, finally the MPP is tracked. So there is interaction between the Simulink platform and the programming platform. So there should be interaction between two. What are the drawbacks, Dr. Bal Mukund Sharma? What are the drawbacks of PSO-based MPPT algorithm? As far as MPPT algorithm is concerned, the drawback, you can say, that is not the drawback. If you are the drawback is, can be said that prior to implementation, you have to find out the optimum value of that
Please
inertia
link
rate.
share हो गया ना? हैं?
Yes. Hello. There is one question.
हम्म?
Vijay, Dr. Vijay. Dr.
3
Vijay.
रिस्पॉन्स आ गया. नहीं तो उसको
हाँ,
वहां
Dr.
से हटा डिलीट करो ना. चैट बॉक्स से हो जाता है.
Dr. Vijay. Can you hear? Dr. Vijay.
Yes, sir.
Can you hear? There was one question in chat box. That's why. That's what
Okay,
I'm.
sir. Okay,
I
okay.
was. So what is Dr. Bal Mukund Sharma is there? What is the drawbacks of PSO-based MPPT algorithm? So the drawbacks is only that before the algorithm is finalized for particular implementation, you have to decide that parameters, PSO parameters, by using iterative process in MATLAB programming. That is the only part which you have to do. So we cannot say that drawback, because you don't need to do it again and again. Once you have decided one system like 375 kilowatt grid connected PV system or any system, you have to decide that algorithm, just feed it into that DSP controller, and that's it. So if you want to find out any drawback and mention, no, there is some drawback, so this is one drawback you can mention. I don't consider it as drawback for practical implementation, practical application.
Thank you, sir.
Okay.
Sir, I think there is no more questions in chat box. Thank you. Thank you for wonderful presentations. Thank you.
Thank you. Thank you for having patience. Okay. So
Okay.
have a good day.
Same to you, sir. Good day, sir.
So should I disconnect, Vijay?
Yes, sir. Yes, sir. Please.
Okay.
Thank
Have
you.
a good day.
Thank you.
Thank you, everyone. Thank you.